So continue the topic about approximating measurable sets with a simpler form of sets. We're going to prove proposition 1.20 in Poland. So recall when the proposition 1.18 talks about 1.17 talks about we can approximate the measure of E using the measure of open interval by the measure of H interval. And we can also approximating the measure of E by using the measure of open sets, which contains E, or we can use by a measure of compact set, which is a subset of E. And then the proposition or statement 1.19 says that each measurable set E can be written as V set minus V N1, where V is a countable intersection of open sets, and N1 is a known set. Or it also says that the measurable set E can be written as H union N2, where H is measurable and where H is a countable closed countable union of closed set and N2 is no set. And so those two, so this also shows that like an important reason that we focus on Lebesgue just measure rather than the Briot measure is because that Lebesgue measure is a complete measure on the sigma algebra M mu F. So it gives a lot, for example, if we are working with Briot measure on the Briot sigma algebra, they don't, the node set, some of the node set is not allowed, and that causes technical issue. But if we work with Lebesgue just measure on M mu F sigma algebra, then all the node set is going to be Lebesgue just measurable, and therefore we're okay. So doesn't cause any troubles, and we can approximate Lebesgue just measurable set E in a very simple form of sets. For example, countable union of open sets, countable intersection of open sets, countable union of intersets, and open sets or compact, very well known simple form of sets. And the proposition 1.20 give us another good news. So proposition 1.20. Okay, I'm going to highlight this and I'm going to. So one important assumption for this proposition is that the measure E is finite. Okay, and then there is this finite union. There exists A finite union of open sets such that finite union of open sets such that measure of E, the symmetric difference, is less than epsilon. So how are we going to prove this? The key idea is to use in 1.17. Okay. So notice that mu of E sum minus A is equal to mu of E. Sum minus A union A sum minus E smaller than mu of E sum minus A plus mu of E A sum minus E. Now let me think, are those two disjoint? AC intersect A intersect EC. Okay, I think those two are disjoint, so this is equal. Okay, so this is equal. And since our goal is to show this is less than epsilon, so as long as we can show, so goal 1, show this is smaller than epsilon over 2, and then go to show this is smaller than epsilon over 2. And okay, so let's think about this. So recall proposition 1.17, right? So what does mu of E is equal to increment summation from 1 to infinity mu of increment summation mu of AJ BJ E is such a union of AJ BJ. Right. So for all epsilon, so given epsilon, there exists AJ, BJ, okay, such that this is smaller than mu of E plus epsilon over 2. And since this is finite, this is finite. So this converges. So there exists n in n, all n larger or equal than n. Sorry, there exists n in n. Okay, and so define A to be equal to the union of AJ, BJ, J is equal to 1 to n minus 1. Now let's try to compute E set minus A is equal to the measure of E set minus union J is equal to 1 n minus 1 of AJ, BJ. So since let's see. So once we define A is equal to this, what's the next step? So eventually we want to prove mu of E sun minus A, right? Okay. We'll observe E sun minus A is a subset of because E is in union 1 to infinity AJ, BJ, sun minus A, right? This is equal to union infinity AJ, BJ. Sun minus J is equal to 1 to n minus 1 of AJ, BJ. And that is equal to n to infinity of aj bj. Okay, so we have this, right? So we have this is a subset of this, therefore the measure of EA with the upper bound is the measure of n infinity of AJ, BJ. Okay. Do we know? Yes, we know. So this is smaller equal than summation and to infinity mu of AJ, BJ, which is smaller than epsilon over 2. And we just need to prove the other one, right? So mu of A sine minus E. We want to show this is smaller than epsilon over 2. And how do we do that? We just let's write down. So again, A is still with a choice. And union from 1 to n minus 1 of AJ, BJ sine minus E. Okay, this is equal to, this is smaller equal than 1 to infinite series infinity AJ, BJ sine minus E. Okay, and that is equal to mu of because E is a subset of union of 1 infinity of AJ, BJ. What we have is we have we can split them, right? AJ, BJ minus mu of E, right? So this is equal to the measure of, oh, and then before, so at the very beginning, so mu, so let's just, so this is equal to summation 1 to infinity mu of AJ, BJ minus mu of E. And this is finite, so we can do this, okay? And then, but this is smaller than mu of E plus epsilon over 2. Oh, and that's why at the beginning, you see that at the beginning, we choose this. At the very beginning, when I was look at the hint, I didn't understand why this has to be so specifically epsilon over 2, because I think this works with any positive number, because we just need the fact that the left side converges. And because it converges, then we can say there exists n such that this is smaller than particular thing. But I was doubt this because I feel like this has no use. But actually I was wrong, because this was used later over here, right? We use this. So everything aligns, and then that's good. So mu of E, and which is equal to epsilon over 2, and we're done, because once you sum up them together, they become epsilon, and that's exactly what we're trying to show. There's the symmetric difference, the measure of the symmetric difference between E and A is smaller than epsilon.